Hi, so now we are just gonna look at how do transformers actually work. So in this section, we'll take a look at the architecture of the transformer models, and then we'll just dive deeper into attention, encoder, decoder, and some more architectures, and a bit of some history, some reference points. So GPT-2 came in like 2019, XLM BERT, and then T5 Albert, Roberta, XLNet, Distilbert, and then 2021 GPT-3, and then these models. This was actually introduced in 2017, transformer architecture. Original research was just on like translation tasks, which was followed by several influential models. That is GPT, the first pre-trained transformer model, which we can use which is used for fine-tuning on various NLP tasks and then obtain some benchmark results. BERT is another large pre-trained model, summaries of sentences. GPT-2 is an improved version, and October 2019, a multitask focused implementation of sequence to sequence transformer architecture, an even bigger version of GPT-2, and Instruct GPT that was trained to follow instructions better, Llama that is able to generate text and variety of languages, Mistral that outperforms Llama across all evaluated benchmarked, and then Gamma 2, a family of lightweight state-of-art open models which are ranging from this to this parameters and are group query attention. Then small language models that achieves impressive performance despite their compact size. So this list is far from comprehensive and is just meant to highlight different kinds of transformer models. GPT is like autoregressive transformer model, BERT is auto-encoding, and then they are sequence to sequence. So basically transformers are language models. They have been trained as language models. This means that they have been trained on like very large amount of data and large amount of raw text in a self-supervised fashion. So this is where the objective is automatically computed from the inputs of the model. They are not needed to label this data, so that is self-supervised. We did not label the data. They are like on their own computing the input, and then they're they are they are on their own computing from the input and then generating an output. So this type of model performs a statistical understanding of the language, but it's less useful for some specific practical tasks. Because of this, the general pre-trained model then goes through a process which is called as fine-tuning or like transfer learning. So the pre-trained model is not uh, perfectly fine for some practical tasks, so that's why we do transfer learning, and then the model is fine-tuned in a supervised way, where we train the model that you have to perform like this. So human annotated labels on a given task. So an example of a task is predicting the next word, having read the n previous words. And this is called as causal language modeling because the output depends on past and present inputs, but not the future one. So my name then is, my name is Sylvain. My name is Sylvain, and then full stop. And then masked language modeling, in which they are predicting a masked word, right? And then transformers are big models. Apart from some few outliers, the general strategy to achieve better is like increase the model size as well as the amount of data. So here, like, see, the model size increased. And then unfortunately, training a model, especially a large one, requires a large amount of data, which becomes very costly in terms of time and compute resources. And it also translates to environmental impact and then CO2 emissions for a variety of human activities. And then this is showing a project for a very big model led by a team consciously trying to reduce the environmental impact. The footprint of running lots of trials to get the best hyperparameters would even be higher. So imagine if each time a research team and a student organization or a company wanted to train a model, it did so from scratch. This would actually lead to huge unnecessary global cost. So that's why we do share some language models, sharing the trained weights, and then we are building on top of it is reduces the overall compute cost and then the carbon footprint for the community, obviously. By the way, you can evaluate the carbon footprint through several tools. This is integrated in transformers. You can just read this blog post. Great. Then pre-training is the act of training a model from scratch. The weights are randomly initialized and then training starts without any prior knowledge. So that's called pre-training. We do have a base model, some this, and compute, very large corpus and days of training, and then we get some pre-trained language model. And this is usually done on a very large amount of data, therefore it requires very large corpus, and then it can take up to several weeks. The training can take up to several weeks. Then fine-tuning, on the other hand, is the training done after the model has been pre-trained. So on this pre-trained model, we do some fine-tuning. And then to perform fine-tuning, you first require a pre-trained model. Exactly. And then we perform some additional training with a dataset that's specific to our task, like our annotated labels. And then wait, why not simply train the model for your final use case from the scratch? There are a couple of reasons. The pre-trained was already trained on a dataset that might have some similarities with the fine-tuning dataset. And the fine-tuning is thus able to take advantage of knowledge acquired by the initial model during pre-training. For instance, with NLP problems, the pre-trained will have some kind of statistical understanding of the language you're using for your task, right? And then they were already trained on lots of data. Fine-tuning will require some less data. And then for the same reason, amount of time and resources. And then, for example, one could leverage a pre-trained model on English, and then they can just fine-tune it on some argsiv corpus, and then that can result into a research or like science-based model. The fine-tuning will only require a limited amount of data. The knowledge the pre-trained model has acquired is already transformed, hence the term transfer learning. So pre-trained training can be done on single GPU. This is easily reproduced, and then we get a fine-tuned language model. And then fine-tuning has lower time, data, financial, and environmental costs, and is quicker to iterate over different fine-tuning schemes. And this process will also achieve better results unless you have lots of data, which is why you should always leverage a pre-trained model, which is like as close as possible to the task you have at hand, and then just fine-tune it. Then general transformer architecture. We'll go over the general architecture of the transformer model. Don't worry if you do not understand some of the concepts. So the model is primarily composed of two blocks. So transformer architecture, we do have two blocks, encoder and decoder. So encoder is the one who's receiving an input, and then it's building a representation of it. Wait, we'll go this to the general transformer architecture in the next video. And yeah, stay tuned. Thank you for watching. Bye. Take care.